Okay, buongiorno. How are you guys doing? Okay, so for today, based on the results of the game yesterday, I think we can use a bit of recap still. Right? I think it's would be a healthy start. So the goal is to just go very quick over some concepts that I think they are worth like refreshing before we move on to like LSTMs, right? So because like as we have been discussing like for the past 5 lectures basically, right? The idea is that we are building like step by step, right? So like all the things that we had to discuss with respect to optimizers and also like the way how we build neural networks. All those concepts, they are still going to be applied for whatever we're going to do in machine learning, at least with respect to the use of neural networks. So those things are very important to have them very like grounded on your base of knowledge on like how to use at least neural networks. Okay. So you guys are very tired of seeing this image of the perceptron by now, right? So if you can just very quickly help me to go over these elements that build the perceptron. So those are the inputs, right? What are X1, X2, and X3 in the input? Those are the predictors or features, right? So those are the predictors or features for one input, okay? What are those weights here? Those are the weights that we train, right? With which goal? Why do we want to train those weights? To try to approximate a y, an output, right? In this case, assuming that the y, it's a single value, what this perceptron will be trying to implement?
A regression.
A regression. Okay. You see that I'm gonna touching all the words that were in the hangman yesterday. So like keep those words in mind. Okay. Good. So if we don't have activation function, we said that this Sebastian, I'm pointing directly to the slide. So if you can see what I'm pointing, let me know.
Yeah, more or less. Thanks.
Okay, yeah. So if we don't have an activation function, we said that this would be implementing a very general function. You guys remember what that would be?
Simple regression.
A simple linear regression. If we have an activation function, that starts to characterize the perception. Is that clear to everyone? Good. Then we realized that the perceptron can do really cool stuff, but has some limitations, right? And like some of them is that, for example, when you need to solve a more complex problem, right? For example, as the exclusive OR problem, you guys remember how the exclusive OR works? So I have like 2 values here that they become to the same class, basically, right? And those 2 in Y, they become to this, they are part of the same class, okay? When I have like a situation like this as the or the AND gate, it's very easy for me to find one decision boundary that can separate both classes. I think that's pretty visual here, right? Like we can clearly see that. And here I cannot do that, right? I cannot find one decision boundary that's capable of separating both classes from me. And then what was the alternative? How do we solve that? You guys remember what we did? Anyone? So we said that like, okay, so I cannot solve that with a single perceptron, but I can start stacking perceptrons, right? And when you start stacking perceptrons, that allows us to make more complex decision boundaries, right? So that's exactly, this is one single perceptron, right? And this is one single perceptron. When I combine both perceptrons, which is essentially what we have up here, right? Then we are able to approximate more complex functions, right? And then I don't remember if you guys, I don't know if you guys remember, but like there was this book from 2015 that the guy basically, he said that, okay, so like AND gates, they are general computation engines, and a perceptron can perform exactly the same function of an AND gate. Therefore, a perceptron is also a general computation engine. So like I can approximate absolutely any function using a perceptron, but not a single perceptron, but stacking perceptrons. And that's why neural networks are so powerful in general, because like in theory, I can approximate any function with a neural network, as long as I'm allowed to keep increasing the complexity of the neural network. And when you say increasing the complex of the neuronal network, how do we increase the complex of a neuronal network? How can we make it more like robust in general? You guys remember what were two of the things that we tried in class?
More nodes.
More nodes. That's a way how you increase the complexity of the neuronal network. What else?
More layers.
More layers. More nodes and more layers. That's basically. Very good. And then that's how we get to like what we know nowadays as the neuronal networks, right? And they go by several names. Some of them that you're gonna find out there in the wild, like the multi-layer perceptron, because that's essentially what it is. It's a bunch of like perceptrons stacked with each others, and feed-forward neuronal networks. Okay, I don't think we need to go over that. Okay, optimization. So for us to be able to train a neuronal network, we need two things. First, we need to define the loss function, right? And why is the loss function important? Because like the loss function basically describes to me like what is my target? How am I trying to approximate like the true value that I'm trying to model, right? So for some of you, like if I'm trying to model like image, I want to approximate the true value of the pixels, right? If I'm trying to do a regression, I'm trying to approximate the true value of like my like rainfall for that month or something like that, right? So like that's essentially like what's the function that I'm going to try to use to try to approximate that value. One that we use quite a lot was this function here. You guys remember what's the name of this function? Mean square error. Great. So like for us to be able to optimize the weights of the network, right? We had to do one little trick here, because this now it's like a feed-forward network. It has several layers, hidden layers, right? And I cannot just optimize directly the weight. I need to compute these gradients, right? And in machine learning specifically, we have like this very cool solution for like optimizing those weights with respect to loss function. What was the name of this method that we use to optimize the weights of a neuronal network? Was also in the hangman last night. Backpropagation. Yeah. Okay. Good. Is that clear to everyone so far? Yeah. Good.
What was the backpropagation do again?
You asked about the backpropagation. No, yeah, -1 point for TB. No, yeah. So the backpropagation essentially stands for computing these partial derivatives for you. Okay. So like I compute how. Let me see if I have that slide of the backpropagation here. Yeah. So you guys remember this slide? So essentially I have the output here, right? So for me to understand how these outputs condition on the weights of my network, okay? For me to understand how these outputs condition by the weight of my network, I need to compute the partial contribution of those weights to my output, okay? And one way how you can do that is by computing these partial derivatives. Clear for everyone? So I'm not going to make you suffer again. I'm not going to try to explain that to you again. But the goal here is that like by inferring by how much I change the output as I make small changes on the weights, I understand how those weights are conditioning my output. Okay, so that's the level of understanding that we need about backpropagation. Because in the end of the day, we have like a very simple way of performing backpropagation in code wise. You guys remember how we perform backpropagation on our codes, both to train the perception and to train the feed-forward neural networks? There are just 2 lines of code that basically implements this whole mess for us. Can anyone tell me what this was? No? But let me go to the code here. Let me see if I have it here. But this is not my computer, so this makes things way more complicated. But the 2 lines that I'm talking about was the one that was called loss.backward, right? You guys remember what the loss.backward was doing for us? I think someone was saying something. No? No? The loss that dot backward computes these partial derivatives that I'm talking about. Okay. After you compute the partial derivatives, right, which is this whole thing here, I need to update the weights, right? So let me go back to that slide. I need to update those weights, right? Because that's essentially what learning stands for. It's basically like, once I understand how my output's being conditioned by my weights, right? And how do I do that? By inferring by how much I'm making an error. So the mean square error is one of the ways how we can do that, right? Based on my understanding of how this is conditioning my output, I can update the weights with the expectation that in the next round of training, this error is going to be reduced. And that's essentially optimization. Good? Any questions until here? Yes, Roland.
So in other words, I'm on the right way if it is going down.
Yeah. Exactly, yeah. Because in the end of the day, right? Let's see if I have this slide here. Okay, yeah. So your loss landscape or your error landscape, in the ideal world, which like we know that's not really the truth, is gonna look like this complex shape. Okay. And why is that interesting? So like if this is your error, right? And you assume that you managed to make your problem to be convex. I don't know if you guys remember like that I was saying convex all the time, you know, like, and I showed you like several tricks how you can enforce the problem to be convex, right? By regularization. You guys remember regularization? L2 norm and so on. Okay, yeah. Anyway, so if that's true, I have guaranteed, like if the problem is indeed convex, that I have one point in this loss function, which this point is defined in terms of the weights of my network. So here I'm just showing W2 and W1. It's like, if it's like a very large neuronal network, you might have like thousands of weights in your network, right? But there is a point where this error is the minimum, right? Which like this, the lowest point of this bullshit, okay? And in this point, the error is minimal, and that's what I'm trying to do during the optimization process. Is try to find the point of minimal error that I have for my loss. Good? Any questions over here? Those are all things that you have seen before, right? Like I'm not telling you anything new. Okay. And that was the stochastic gradient, basically what we just described here, right? And then I told you about other optimizers. You guys remember any other optimizer? One that we use all the time too? I told you about my favorite optimizer. Which one was that? You guys are breaking my heart.
This one for something
Adam, yeah, there, okay. Which I didn't put here, but yeah. So Adam tried to solve some other issues, right? So for example, you guys remember what's the problem of local minima? What was the problem that was like, okay, all we're trying to do is to make sure that we don't get stuck in a local minimum, because the local minimum, it's a place where the derivative is also equal to 0, right? And if the only criteria that we use to say that we found the point of minimal error is the derivative to be equal to 0, I might find like another point in this loss function, because the loss function is very complicated, right? In reality, the loss function looks like a mess like this, right? I might get to other points where the derivative, you guys remember what's the derivative, right? It's like this slope that only touches the curve in one point, right? The derivative is also equal to 0. So like we said, okay, so we need other strategies to make sure that we are not stuck in that point, right? And some of them were, what was one of the things that we said that we could add? You guys remember the analogy of the ball rolling down? Momentum, yeah. So like the momentum is one of the things that were added as an alternative to avoid getting stuck in local minimums. Okay, good. So all those things that we discussed so far, they all apply to what we're going to do today. Okay, I just want to make sure that you guys remember what the optimization stands for, like the architecture of neuronal networks and so on. But in theory, even if you didn't attend the course, you should be able to follow this tutorial today. So what was the package that we were using for the percept to implement the perception and the feed-forward neural network? PyTorch, right? So today I'm gonna go with you guys with a different package that's as popular as PyTorch, although PyTorch is by far the most popular nowadays. That's the TensorFlow. So TensorFlow, I think they're still being kept updated by Google. PyTorch is like a Facebook child. So like you have those two mainstream, but by no means they are the only two packages that you can use for neural networks, but they are the most popular ones. Okay. So I ask you guys to install the TensorFlow. Did everyone do that? No? Okay, yeah. If you didn't do it, you can just follow the tutorial like as I go over the Jupyter notebook. Okay. So one thing that we have been doing so far, right, is to can I zoom out in this thing? Yeah, better. So one thing that we have been doing so far is to assume that the features of our data, they are like the samples of our data, they are indefinite observations, right? So like each row on our table, we assume that they don't necessarily have a correlation with the other rows on the table. They are independent observations, okay? And that's fine, right? But what if those observations they actually correspond to like something that was done, several measurements of the same thing? So for example, essentially what we're describing is a time series event, right? So for example, if I have one point of measurement, one gauge or something, that's measuring rainfall, for example, in a specific location. Did you want to work on that? I think the other door is open. Okay. Sorry, I thought they were trying to leave. Yeah. Yeah. So good. I think there is one question here.
Yeah, it's just when you move away from this microphone, it's getting a little bit.
Yeah. Okay. I'll try to stand here.
Thanks.
Right. Let me close this. Yeah. So yeah, which we have been considered that they were like independent observations, but what if they were time series, right? So can we use simple feed-forward networks to analyze time series data? You can, but there is a little bit of work that you need to do in order to get your data to fit the structure that's being expected by neural networks. And essentially, we're gonna go over that, okay? So one alternative that's like quite popular when you're dealing with analyze sequential data, right, is that instead of like feeding in your observations as independent samples, right, which is essentially what we are doing here, right? So here we have like the regular by vanilla neural networks is you can understand that's either like a perception or a feed-forward network, okay? And X1 here, they no longer stands for features, but rather samples. Okay. So like here you'd have like one sample X1 that goes through a feed-forward neural network and spits out a result to you, right? Either a class or like a value, like in case that you're doing a regression, right? But now if those samples, right, they are actually connected to each other by a temporal component, right? Another alternative is to use one thing that it goes by the name, like as the general class, the recurrent neural networks, right? And the way how it works is the following. You still have your independent observations, right? X1, X2, and X3, which no longer are independent because now they are like observations of exactly the same event, just going over time, right? And now you have two networks that kind of work in parallel, okay? One is going to take in consideration the input that's being provided, and another one that keeps track of previous states, like our previous observations, okay? Which is essentially what this H stands for in this case. The H you can consider as being hidden. Some people like to refer to H as the hidden. And what it does is the following. So imagine that like this is a sequential observation, right? You have an initial state most often, which could be either observation or just like a random value. This observation is going to be combined to the new observation that you have. Okay. And here you have one set of weights that you train that are specifically trying to understand which type of information from the previous observation you should keep when you're trying to make the next prediction, which you can imagine that's like very intuitive, right? So for example, let's say that you have let's say that you have observation that is supposed to be continuous, right? Something that should look like this. I'm going to use y, and this is t, right? So let's imagine that you have phenomena that kind of works like that. I don't know what could be something like that, maybe rainfall. Like you don't have like huge jumps in rainfall, like because it kind of depends in the season. I think you guys tell me, but I think it should, right? So you don't expect this continuity, right? Like it's very difficult that you're going to have something like that instead, right? Or you shouldn't at least. Sebastian, can you see stuff that's right in the blackboard?
A little bit.
Poor guy. Anyway, yeah, but I'm just talking about this continuity here. So if that's the case, by adding information about the previous time points, at least should avoid you having these discontinuities, right? So it is desirable, if that's the type of properties that you're trying to mimic, that you should take in consideration previous observations, and that should kind of steer the direction of where your next prediction should go. Are you trying to put the volume on or the margin? No, yeah. Okay, yeah, I'm just gonna move that to the other side. But so what I'm trying to say is that like by using this trick, let me do this so Sebastian can see. By using this trick of like adding information about the previous state, you also prevent this type of like discrepancies on your data, like these huge discontinuities, okay? And that's usually beneficial because if you get a prediction, if you have a model that says like, okay, I had 100% in one time point, and then I have 2% in the other one, there is definitely something that's wrong. And by linking the previous observations, you avoid this kind of discrepancies. Is that sort of clear? Like, why is it beneficial to take in consideration previous times points when you're trying to predict the next ones? I hope this is sort of intuitive to everyone, but if there are questions, okay. And then we just keep going with this process, right? So like now we have a new observation, right? That's gonna steer the output of the next node, right? So like that's the new state that's gonna be output, which is also dependent on the previous time point. So like when I'm trying to predict t equal to 1, so like that's the next time point, I take in consideration the features that are associated to that observation, which are x1. So like just for example, again, if you're talking about like rainfall, right? So like I have all these features that are associated to my measurements of rainfall. For example, what are some of the features that are usually associated to rainfall? Could be the time of the year, perhaps humidity, like atmospheric pressure or something like that, right? So those are a few features that could be coming through X1. And in this case, if you're talking about rainfall, so if my output is rainfall, what could be the previous output that I'm trying to incorporate here? What would be my H0? Zero, but in terms of like what type of information is H0? It's also rainfall. It's also rainfall. Okay. Good.
But it starts with zero value.
Or could be a random state. Yeah, the idea. Yeah. So like because in physics we had this thing about the initial value problem, right? Which like for you to be able to tell me exactly where the ball is going. I throw a ball right on the floor. For you to be able to tell me where that ball is gonna be, even like the speed of that ball, you have to know where that ball starts from, right? So like that's essentially. Yeah, sorry. Yeah, that's essentially the initial value problem. Okay, and it's the same here. So like until we have a very first observation that's like good, right? It's very difficult for me to start training the network. So usually the first sample is like just like a starting point, initial value. Okay, is the problem that we're trying to solve here sort of clear? Is everyone on the same page with respect to how this is different from the previous case that we're trying to solve with perceptron and fit for neuronal networks? Yeah, okay. Yeah.
If you are working with some measure that you expect to behave like this, is this type of models still useful to detect?
That's a great question. Yeah. So so you're saying like in case that you're expecting, in case that you're expecting discontinuities, right?
Yeah.
So that's true. And for example, there is one type of data set that's highly discontinuous, which is like natural language processing. I don't know if you guys are familiar with the concept, but essentially like when you're using your cell phone, like either like an iPhone or one of these Google Pixels, you see that you have the next suggested word for you, right? Has everyone realized that? So you see like the option, and usually it's pretty good, right? Like quite often you just need to keep like accepting the suggestions. So language in general is very discontinuous, right? Because if I say, the book is on a lot of people are going to say table, but like the book could be on the desk, could be on the floor, could be anywhere, right? But like the highest likelihood is going to be the table, right? So LSTMs, although language is still sequential, right? Because I told you the book's on the table, you have an internal model in your mind that's like, okay, most often this is associated to the table, the next word, right? But it's very discontinuous because I have several other possibilities that are also realistic, right? So LSTMs, they don't work well for this kind of thing. And why? Because LSTMs are expecting to model something that's sort of continuous. Okay, so if your data is highly discontinuous, maybe LSTMs is not the way you want to go. And there is like more modern techniques to solve that, it's really far away from me being able to cover that on this course, but it's called transformers. And I can show you some more resources on that. But it's a great question. Any more questions? Yeah.
If you're interested in modeling land cover or land use change,
then
you could expect a sudden change from one type to another.
But in this case, if it's land cover, right? It depends a lot on how this data is structured. You're talking about land cover over time. Yeah, so if it's land cover over time, imagine that like you have a satellite picture of I don't know, like a place that you're monitoring, right? If the process is not entirely human-made, because humans really like mess up with the landscape, but like let's say that's a natural process of erosion or something like that. Usually those processes, they happen kind of in a smooth way as well, right? Like from my understanding, right? Like that is things they don't change from day to night, right? So nature in general tends to be more smooth, like more continuous. Like humans, they make the thing very discontinuous, but like in general, like if you're talking about changes in landscape, let's say that you have several pictures of a piece of forest or something, the changes, although there are changes, they're very minimal. So like you should be able to still model that as being sort of a continuous event. Any other questions? And then actually that triggers like the combination of several methods that we discussed as well. So for example, if we're talking about modeling time series that are images, one popular way of doing that is by extracting features with convolutional neuronal networks, which we saw together, right? You use convolutional neuronal networks to extract features, obtain a vector representation of that image. And then from there, you can use LSTMs to model the incremental changes. It's a pretty cool project as well. Like, yeah, I have seen people doing that. Any other questions? No? Okay. So LSTMs, they are a little bit more sophisticated than the general recurrent neuronal networks, okay? The recurrent neuronal networks, they basically implement this thing that we were discussing before, okay? Which like essentially trying to combine the features of these new inputs that you have, X1, to the previous observations that you had, which is the H0, okay? And use that to spit out like the new result. And then this hidden state is passed along to the next observations as like my new initial condition, okay? So if we can compare the recurrent neuronal network, right, to the LSTMs, the recurrent neuronal network would sort of look like this, which is essentially what we described above. So here we have the observation xt minus 1, right, where t here is representing the order of my observations, okay? These previous states passed along to the new cell, where I combine with the current observation that I have. So like that's my new sample, right? That's coming from a future time point. These lines here in black, you can understand them as being the weights of this network that we trained before, just as we did here. But just to avoid like overwhelming the diagram with too many notations, these black arrows that you see, they basically are representing the weights of a network. So the same way how we're looking at the here, right? So like here, each arrow also represents a weight, right? So the logic is the same here. Okay. So now after you have done that, after you have combined the information that's coming from this new observation, the features of this new observation, with whatever was the previous output of the model, right? You combine then via integration of like neuronal networks, right? So like by multiplying by those weights, and then you have an activation function, just like as we had before, right? Which is gonna give me the new state of this phenomena that I'm trying to model, which in this case could be like rainfall or like pollution or whatever, okay? But now you see that the only way how I can make a predictions if I take all the observations that I have in the previous state as being equally important as the observations that as the features of this new observation that I have, okay? Which not all the time is beneficial, right? Let's say that I have a phenomena that has several features, right? And in some case, just like as random forest usually does, if I have a specific pattern or like something that's like it's a feature that matters a lot, I can afford to drop some information that's in other features that might just be bringing noise, right? So that's one thing that random forest does for us, and that's why we are so interested in like the future importance, right? That's why we call it that. Because like at the end of the day, if that feature, which I know that matters a lot, is telling me that, oh, definitely that's what's gonna, that's what should be our prediction or like the value that we're trying to regress. So if that's the case, it's beneficial for you to also learn which elements in the sequence, which features of the sequence you should discard, right? And that's one thing that LSTM has different from the recurrent neuronal network. Because here, let me try to zoom in a bit more. Here, perfect. Here I have a diagram that's so here I'm just zooming in on this cell that's exposed, okay? And we have like these other functions that are implemented inside of a LSTM block that basically tells me which information I should forget with respect to what just came into the cell. So for example, which information from the previous output that I had, I should just discard, right? When I'm trying to predict the next state. I also learned how I should be taking consideration the features of this new observation that I'm taking in, which here is the XT, okay? And then I have another network that's just trying to learn how to combine all these elements from the previous observation, which here stands for the H, right? And the new incoming information. So in LSTMs, we call that as the input gate, which is represented by the I, right? which again, basically represents what information from these new samples that I'm observing matters for my, the state of my next prediction, right? Then we have the forget gate, which stands for the F here. The forget gate says like which information I should discard from my previous observations, okay? And then I have the output gate, which collects all this information from the input gate and the forget gate in order to make the next prediction. Good? Any questions until here? I know that the diagram is a little overwhelming, right? Like there are all these like symbols and everything, but the only thing that I wanted to realize is that in the end of the day, those are weights of networks, right? So that's essentially what we're doing before. This observation, it had, let's say that was a regression, right? So my hidden state here would represent a single value, right? And I'm trying to learn how I can consider what's the weight that I should associate to my previous observation when I'm trying to predict the next state. Okay, so that's essentially what this W would be doing. X here is my input, right? So I'm trying to learn a set of weights that should tell me how I should combine the features of this new observation that I have. Okay, so those are networks. U and W are networks. X is the new input, and H is this hidden state. That's in this case would be representing like my observation over time. Questions until here? So here, the C usually stands for like what's the cell state. Okay, so the cell state is something, the H is the output, right? So that's the thing that like I'm gonna actually use as a predictor for that specific time point, right? And the C state is something that I pass along for the LSTMs. So before, as you remember here, the recurrent neuronal network was passing the H, right, both to the next cell and as my output. Now the LSTM is associated the two of them. Here, the LSTM is associated the two of them because I don't need necessarily my output to be the thing that I pass along. For example, if my output, let's say that was a regression, if my output is rainfall, I have one single value to pass along, right? But let's say that like I might find a representation for the cell that's like higher dimensional. So let's say that like I'm passing like a vector that has 10 elements, and those 10 elements, they sort of summarize all the states of the cell, right? Just like as we had the hidden layers before. The hidden layers per se don't have like a meaning, right? But we assume that they're encoding information that's representing the inputs layer, right? So instead of like just passing one single value, we should be passing the HT. I'm passing the state of the cell, which is like this hidden state, which is supposed to include way more information than just a single value. Is that clear? Like what's the rationale of passing cell state instead of just passing the H, for example? Questions? No? That's the difference between Zoom, because I see that you guys are confused now. Maybe hopefully this is gonna get more clear once we get to the code, okay? And what you see here basically are the activation functions, right? So like as we were doing before, we are combining the input, like finding a way of combining information that's in the input by learning a set of weights, and then passing that information to an activation function. So it's like exactly what we have been doing with feedforward networks, right? Okay. Yeah, please.
So with the starting information, sort of optimization that as well, how do we decide what we can run and what we can start?
How we decide what to pass the start state?
Yeah.
Yeah, also by
What happens, what's target there? You have to do a function of access to say.
so the cell state is just like the same thing that we had in the hidden layer, right? So like the hidden layer per se, we don't optimize the hidden layer to mimic anything. The optimization is always with respect to how the loss function is defined. And if you guys remember the loss function, it's always like the output which in this case is H, not CT, right, is the output with respect to what's my desired target, right? So like, as we have been saying, like these outputs should mimic, and that's the output that I use for optimization. These outputs should mimic whatever I'm trying to model, like either like for in terms of classification or in terms of a regression. So that's the thing that I optimize. This C is going to be learned as like, I want to make sure that this hidden state is not messed up, right? Because this hidden state C is conditioning my output H. So like this whole thing is supposed to like all these weights that are being trained, right? They should make sure that the H is meaningful. And the CT, we assume that's going to be meaningful because the CT is also conditioning 8. So therefore, we assume that CT is meaningful as well. Okay? Questions? But you're going to see that the most complicated part is always like trying to understand what the thing is doing. When you go to the code is extremely simple. So like that's why I'm affording to spend that much time like explaining how LSTMs work, because the code is trivial. You know? For example, the backpropagation, right? Like I made you guys understand how backpropagation works, but in the end of the day, you just do loss.backward and optimizer.step. That's it, right? So like, but it's always important to understand how things are happening under the hood, right? So. Okay, 5 seconds to questions. Sebastian, are you still there?
Yes.
You have any questions?
No, not any. It's still hard to follow, but
which part's hard to follow? All of it?
Yeah, I mean, it's very theoretic and yeah.
Okay, yeah, we're gonna get to the application in 10 seconds. Okay. Yeah, one last question.
Are they adding up the same, they're like shares of the current information and existing forward learners, right? So they're adding up the same.
Yeah, they are combined. Yeah.
Combined to get the whole information.
Right. Yeah. Both the information that's being propagated through the F and through the input. So like that's the forget gate. That's the input gate here, right? They are merged into this C stream, right? So the C stream is here, like saying how much of the previous state I should forget. So I don't know if you guys are familiarized with the concept of masking. I think so, right? Like what means masking of like your data? For example, in image, masking means like multiply by 0 things that you don't want, right? So like, yeah, okay. So it would be essentially the same. So I'm masking things that I don't want. That's what the forget gate does, okay? The input gate, it's responsible for giving weights for the different features or predictors that I have in the new input, okay? All this information comes to this stream. So you see that they're being combined here, right? And then from here, it feeds into the output gate. That's going to be the one that says like, okay, so how do I combine this information now that's coming like from the input gate and forget gate to make the next prediction? So like, yeah, all this information is being used for the prediction of the output. Okay. I think now we get to the code then. Here there is a little description in case you guys need a little refresher later on. Okay, yeah. So I tried very hard to find like a realistic data set that we could potentially use for the tutorial. Most of them, and thank you also for helping, but most of them demanded too much pre-processing and was not like good for like for this class. But like I found this climate change plot, right, which basically says how much the temperature is changing over time. Here are the years. So I realized that this part of the plot here kind of has like a trend, like with some oscillations, you know, and I was convinced that I could perhaps say that the data from 1960 to 2020 can be sort of represented by this trend that we have here. So for those of you who saw the previous class, it's exactly the same data that I had for the other example, but just because it looks a lot like this trend of temperature over time, I decided to use the same data, but now we are going to say that this is temperature anomaly instead of number of passengers in an airplane, okay? So, but the data is exactly the same. So if you have seen the previous tutorial, you're going to see that the tools and the ways how we're analyzing this data is the same. Okay, so what this data here represents to us. I told you that, for example, we could have several features that are associated to one observation, right? So for example, we are talking about rainfall and like some of the features that are associated to rainfall. We talked about humidity, temperature, and like I bet you can think of another 20. But in this case, I'm just taking consideration temperature. So like I only have one feature in this data, okay? Just for the simplest of the case. And then once we go over this tutorial, I'm gonna give to you another data set that's a pollution data set that has more features. And then that's gonna be the exercise associated to this tutorial, okay? But like for the simplicity of the examples, we're just gonna use this data set, which is fake. So that's not real climate change data, okay? And yeah, and then you guys are gonna play with like multiple variables there. Okay, so that's the data that you can load using just like the Panda read SVD, that CSV that we have been using so far, right? That's how the data looks like once you load it, right? So like here you have information of the year as not just the year, but like it would be like month of the date associated to that measurement, right? And by how much it changed the temperature, right? So you see that's like it's a relative to increments here, right? It's not absolute temperature. Okay, so the first thing that we do is to do this normalization, right? Like it's always the very first thing that you do. Like that's the first thing that I do myself is to do like a little inspection of the data, right? Try to observe if like the different features, they have huge discrepancies, right? And that's one thing that we are doing before. Since here I have just one feature, basically stands for normalizing this one feature that I have, which is the temperature, right? Very good. Okay, so the range, I'm mapping it to be between 0 and 1. Okay, so the fit transform here basically is going to get this data that is like in its original range. That was not much because the incremental changes in temperature here, they are kind of bounded as well, thankfully, right? That means that we don't have that huge change in temperature, although 1 degree seems to be a lot already. So fit transform, you guys remember what the fit transform does here? So the fit transform is going to actually map the data from the original range, should be between 0 and 1 in this case, okay? Then next, I do a separation between training set, right, and test set. And why is that important? Someone answered the question yesterday. I think it was you, right, Florian? So, I don't know.
Actually, I think it's important to have like a trace and test at the end, so that you train the data at the end. So good result.
Right. Yeah, exactly. And that's essentially the same goal that we have here, right? In this case specifically, the separation between training set and test sets is going to be done in terms of using the first chunk of the data. So like about 76% of the samples, 67. Let me try to zoom in this thing here because I can't see from far away either. Okay, yeah, 67% of the samples are going to be used for training, and the remaining is going to be used for tests. So you can see that like you're just using the first part for training the model, and then you're going to see like how the model behaves in the second part. Okay, so by now you're very familiarized with this type of notation, right? So like we're going from 0 to train size as like selecting the first features of the first time points of the data to be part of the training, and the remaining, which means like train size to all the way to the total length of the data to be the test set, right? So I think you guys have no concerns here, right? Okay, great. Very good. Let me see if I explain this. Okay, so now one of the things that are very important for us when you're trying to organize the data in a way that we can feed into the recurrent neuronal networks and the LSTMs is to format this table, right? So like in a table that looks like, in a data that looks like that, what are the inputs and what I'm going to use as output, right? As the predicted value or my target, right? So the logic is the following. My input is going to be the value in time t, right? And time point t, and the output would be t plus 1, okay? If I want to use more observations back in time, right? I can say that my inputs are going to be t minus 5, t minus 4, t minus 3, t minus 2, t minus 1, and the output would be t or t plus 1, okay? So, but you see that the data originally is organized like this, right? So I need to create a new table out of this table that's going to organize my data in the way that I need, which would be like predictors, right? By target value, okay? And that's essentially what I'm doing in this function here. Okay, so the inputs to this function, so that's the function that I'm calling like create data set, okay? And the look back tells me how many features or like how many time points in this case I want to use as my input for the model, okay? So let's go over that together. So here, this is the index, right? That represents basically like where that observation is in time, in this case, right? And here is the until which point I'm gonna take, right? So like if I'm going from I to I look back in this case means like how many samples I'm taking ahead of me, right? So maybe I write it down. Maybe it's easier to you don't have anything, right? So we have this data, right? So here we have time points. Can everyone see what I'm doing here? I don't know if the light is helping out. So this is T, right? And this is my observation. I'm gonna call Y. That's the output that I'm trying to do, right? So one way how I can, this table originally is organized as T by Y, right? Because that's a single variable. Good. So for me to be able to use more time points in the test, let's say that I want to use the previous 4 time points in order for me to predict this t equal to 4 here, right? So now I need to transform this table into something that sort of looks like this. T minus 3, t minus 2, t minus 1, and then finally predict t. Okay, so that's essentially what this function is doing for us. Is that clear for everyone? And once I have these, you see that like I could even use like a simple neuronal network to solve that, right? I use our random forest. I could use these as your predictors, and you use these as the target variable that you're trying to model. Okay, but we are assuming that like recurrent neural networks they might be beneficial. Why? Because we assume that there is a smooth transition. There is some degree of continuity between like these observations that I had in sequence, right? And that's essentially what the LSM is doing in this work. Yeah.
So we have one table for each observation as a result of that.
So for each observation in this case, right? So like for,
This is the table
yeah,
representing the T0.
these
One complete moment.
yeah, this row will be representing T4, right? So you guys remember that, yeah. Okay, yeah, and I'm using the previous time points as the features.
Okay.
Okay. Is that clear for everyone? Like what's happening here? Any questions? Okay, cool.
So Antonio, where is Y in that table down there?
Because
You don't need that in.
because this y, right, like in this case, would be y of t, right? So like this is y of t is 0. Let's call it this. Because if this is a function, right? So this will be y of t1, right? Okay. So this is y of t minus 3. This is y of t minus 2, and so on. And that's y of t. I wrote t, but it's the y of t because it's a function, right? Okay. Any questions? Sorry, Sebastian, I had to use the blackboard. I know that you cannot see.
I will figure out.
Okay. Any questions? All right. So that, yeah.
The number of observations back is flexible.
It's essentially what this look back, you see this parameter look back is doing for you. By default is 1. So essentially it would implement like what was my before, and I use the next as my output. But the look back, it's something that you can play with, and we are gonna do like in this tutorial. Okay? Good? All right. Okay, so in this first part, we're gonna use the look back equal to 1, right? Which basically says like use my y of t0 to predict y of t1. Okay. So now we finally get to the point where I start implementing the LSTM. Before I move on to like implementing the LSTM, is there anything pending with respect to like what's the problem that we're trying to model, the need of like formatting the table? I hope that's all concrete on your minds, but like let me know if you have any questions, okay? So in this first part, we're gonna use a look back equal to 1, right? This is gonna create these data sets for us. Like train here is the segment of the data that I'm reserving for train. That's the first chunk of the data. And test is the second chunk of the data, okay? Test X and test Y, they are basically like the same data shift, because you can see that's exactly the same data, but shifted in time, right? So you can see like what's the format of like what are some of the observations that we have. So for example, train X here. I'm plotting just the first 5 elements of train X, okay? So train X, the input was 0.015, the output was 0.027, right? So like previous point to predict the next one. Now you see that the next sample is the input 0.027, right? So like, it's just to give you an idea of how this data is organized. Very well. So now we're gonna see how we implement neuronal network, more specifically the LSTM, using TensorFlow, which is something that you guys haven't seen so far, because like you're all familiarized with PyTorch at this point, right? TensorFlow, some people really like TensorFlow because TensorFlow, it's very intuitive the way how you create like new layers and like how you add like activation functions and so on. The very first thing that you do in TensorFlow is to create a model that's sequential. Okay, so you say, okay, from now on, I'm going to start stacking things that I would like my neuronal network to do, right? In contrast to PyTorch, like if you guys remember, PyTorch, what we had to do was to define first what were the elements that we're going to use, right? So you guys remember the NN linear, which basically stands for like a linear layer. Then we would define the hidden layers, what were the dimensions of the hidden layers and so on, right? And then you're going to describe what the forward is supposed to look like. So like, okay, go through the input layer, then go through the hidden layer 1, hidden layer 2, and then finally output, right? The way how TensorFlow does that is like you start with an empty template, which is the sequential, and then you start adding stuff to your model, right? So like the very first thing that you're gonna add it's a LSTM block, okay? The LSTM block, it's basically what we defined up here. So that's one LSTM block, okay? Now, how we pass attributes to the LSTM block? So the first argument stands for how many blocks I want to use, okay? So let me go back here. Here I have 3 blocks of LSTM, for example. I'm defining 4 down there, okay? But essentially stands for like how many blocks I'm gonna have. Okay, and since I'm doing a regression, okay, you guys remember the fully connected layer that I would like, the way how it would go is like the very last element that I'm gonna have, if it's a regression to a node, right? And it's exactly the same here. So I'm gonna get the output from the LSTM and give it that as input to this dense layer. So like it's gonna get like whatever is the dimensionality of my output, right, from the LSTM block. Note here that I don't need to worry about what were the dimensions of the output. If you guys recall, like when I was designing the feed-forward neuronal network, I had to care about what was the output of my linear layer, right? Because it was input and output dimension. You guys remember that? And then I had to make sure that like this output dimension was matching the dimensionality of the next linear layer. So that was out 0 and that's going to be out 5. Right? So like we had to care about kind of stuff. And with TensorFlow as well. TensorFlow just assumes like, oh, it's sequential. So like, I'm going to make sure that I take care of that. So like in 2 lines of code, we design an LSTM that does a regression, like simple like this, you know? And that's why some people really like TensorFlow because it takes care of everything for you. But the trade-off is that you lose flexibility, right? But like, yeah, it's fine for simple modeling that take care of the job. Okay, so what we used to do next, right, is to define what are going to be the loss functions that we're going to be using, right, and what's the optimizer. So although the let me point here, the syntax is slightly different, the rationale is exactly the same. So now I'm going to say how I'm going to train this model, right? So since it's a regression, like one of the type of loss functions that I might use is something that computes based on the error, right? So I could use like mean absolute error, but just for the sake of like being consistent, I'm going to stick to mean square error, right? So you among the library of losses that you have on the TensorFlow, you can very easily just say what it is that you want to compute, which is different from PyTorch, because PyTorch you had like to import a loss function. I don't know if you guys remember when you're defining criterion, you say like n dot MSE loss and so on, you know. Here you just say like, it's just mean square error. In the optimizer, what's the type of optimizer that I'm using here? Stochastic gradient. The next parameter that I need to pass for the stochastic gradient was the learning rate, right? You guys remember what the learning rate is for? The learning rates conditioning, like how I try to approximate this point of minimal loss, like minimal error in my loss function, right? If the learning rate is too big, what's usually the effect of that? Super jumping, right? If the loss function, if the learning rate is too small, it might take forever or just not converge at all, right? Because like we take this very, so the process of setting the proper learning rate is still a little art. And like you guys remember that we had these for loops, like testing different combinations of like hyperparameters, right? So that's something that you also can do here. So you can put this whole thing inside of for loop that keeps varying the type of learning rates that you want to use. Very well. Now that we have defined all the parameters that we need to train, right, the model, which is basically the loss function, the type of optimizer that we want to use, the model has been defined like right above, right? Now we can finally move on to training this model, okay? And the process of training with the TensorFlow is also simpler than what you do with PyTorch. So basically what you do is to feed in as first parameter, the training set that you have, right? So like what are the predictors that you have? In our case, the predictors in this case, it stands for like using y of t minus 1 to predict t, right? Like predict the states in the next time point. The next parameter is the labels that are associated. In our case, because the regression is like the prediction of the next, the temperature in the next time point. Next, you have the number of epochs that are going to be used for training. What are the epochs? Number of iterations that you're going to keep trying to optimize your set of weights, right? The batch size is something that I don't think we did together, but like the batch size basically stands for how many samples, in this case, how many rows of your data you're going to use to try to predict in one pass, right? Here I'm using just batch size equal to 1, so that means that I use one row to predict the output of that row, then I move on to the next row, predict the output of that row, okay? But like another alternative would be to use like whole segments. Yes.
How do you actually define the batch size? Because I didn't do that so far. I don't know. Just default one anyways, or is it?
That's a good question. Let's see what's the default for the batch size.
Is the value between 0 and 1?
No, the batch size is a value between 1, which is the minimum that you have, right? It could be as big as the whole data in one pass, okay? But I don't know what's the default for batch size. Let's see. Oh. Well, this is going to take a bit more time, so we do later. But like, yeah, I bet the batch size also has a default parameter and probably is 1 anyways, yeah. But yeah, so verbose, it's another thing that we didn't have back in PyTorch, which basically stands for like during the training, throw me like some information about how the training is going, right? What we used to do before was to actually put like a line of code where we do the print of how the loss function is going, how the accuracy is going, so in some case, right? So that's something that you can control via verbose. Verbose equal to 0 means like don't plot anything. I just want the final result. Verbose equal to 1, it gives like step by step what's happening, like what's my current loss, the value of my loss and so on. Okay, now you can do the validation in the same epoch, right? So you guys remember that we had the first chunk of the data that does the training, right? Then what you do next was to do like with torch no grad, because we were saying that like, okay, from now on, for the evaluation of my model, you can drop like all this information that you use to compute back propagation and so on, because I don't want you to train on the test set, right? So I had to manually turn off all those things in PyTorch. You guys remember that roughly, right? So if you go back to the codes, you're going to see like model eval, right? Which like we changed from training mode to evaluation mode. And then next would be like with torch no grad, which means like don't do back propagation in this segment of the code. But like in TensorFlow, you can just specify directly what's your validation set. And TensorFlow understands that you don't want to train on your validation set. So like, you see, all those things that we used to do like in whole lines of code in PyTorch, it's summarized in one line in TensorFlow. Okay, so like TensorFlow is easier to use in the end of the day, right? But you guys start to need the right points. Like it's easier to first learn the hard way of doing things, you know. And I prefer PyTorch. Okay, so all this information about the training is stored in history. So the history in this case is keeping all this information about the loss function, the loss value for the training set, the validation set, in case that you also have like some other metrics that you can specify, for example, what's the R square, all those things, they would be all stored in history in this case, okay? And then you can plot like the things that you have in here. Since here in the way how I set up the training, I only said that I was going to monitor the loss function as the mean square error, right? I didn't specify anything else. So the two things that I have in history are just the loss for the training and the loss for the validation set. Okay, so those are, but if you have more things that you can add, as like all these other metrics that I told you about, you'd have all those keys listed for you on history, okay? And then you can make as many plots of it as you want. So like, yeah, TensorFlow really takes care of business for you. Like, you don't need to do anything basically. Okay, so like here I have a couple of functions that we're gonna use just to inspect how the model is training, right? So for example, here, as you can see, I'm gonna get this information that's now stored in history, right? To make the plots of how the loss is changing over the epochs for both the training set, which like here is loss, and for the validation set, okay? And then I'm gonna make some cool plots with that. The next function, okay, it's make preds, okay? So once you have trained the model using model.fit, right? Now you can make predictions of your model, right? Which as simple as like model.predict, and then you say like which one is the data that you want to use to make those predictions, right? So we have trained on train X. So we expect that like the performance with train X is always going to be better, right? And then you're going to do the prediction also with test X. So like that is the segment of the data that was not used for training. After we have obtained the predictions, right? There is one thing that I realized that we didn't do like in the previous tutorials, right? Which basically we use these scalar operations to like normalize the data. But I think in no point I actually did the inverse operation, which like you guys should have told me that I didn't do that. So like once you make the prediction, you want to put your data back to the original range, right? Let's say that like you have this feature that is going from 0 to 1000, right? Originally, you do the normalization to put it between 0 and 1. Now, if you make a prediction with that data, right? You're gonna get the prediction also between 0 and 1, right? Which like is meaningless for you because you're trying to predict something that's in the range of 0 and 1000, right? So you need to do the inverse transform to put it back in the original range. You see why is that important, right? In terms of like prediction per se, doesn't matter as much, but because like you can still make an inference of how the model is performing because it's like L2 is normalized, but it's a linear operation. But in the end of the day, if you want to deploy that model out there, you have to make sure that it's like making predictions in the range of the original domain of the data, okay? So that's a very important step that I didn't do like in the previous tutorials. Very well. So yeah, here we do like a little computation of the root mean square error, right? Between what was the prediction and what was the actual data, right? Our like the actual temperature that we're trying to model. We do the same for, did I just repeat? That's R square, right? So like what that's just to compute the determination coefficient between the predictions and the or original temperature values. And that's basically it here. Then we do the same for test. Okay. Right, and this function here is just gonna plot the prediction overlapping, this plot spreads plots the prediction overlapping on the original data, which you're gonna see in a second, okay? So that's how this plot looks like for this model that we defined up here, right? So here we defined a model that was going to train using stochastic gradient with learning rate 0.01, using 4 LSTM blocks. The output would be 1 because we're doing a regression in the end of the day. So you're just trying to predict this one value of temperature for each one of these observations, right? And that's how it looks like. So you see that the validation loss is going down as expected. So the model is effectively learning something. The training was originally pretty low, but I hope you can see that there is still a little slope here, right? So like this is still good. That means the model is effectively learning. Now the make preds tells us how the model is doing in terms of like root mean square and R square. right? And what we see here, that's like the performance doesn't seem to be great, like numerical terms, right? But let's see how this model performs like when you overlap the data. The original data is the one in blue, right? The data in orange is the segment that you're using for training, okay? And the model in green, in the part in green is the parts that we are associating to the test data set. Okay, so that's the one that was not used for training. So you can see that the orange one, which is the training, it's basically overlapping pretty good, right? Am I in front of you guys? Okay, yeah, it's overlapping pretty good there. And the performance for the test set is not that great, right? So like there is still like a greater degree of error here, as pretty much as we got summarized here by the metrics that we're following before. Okay, which kind of expected. So like most often that's what you see, that the performance for the training set is always better than the test set. Okay. So what have we done so far? Let's summarize, right? We designed a LSTM model that had 4 LSTM blocks on it, okay? So they kind of count as like the number of hidden layers that you have. We are performing a regression, so we got like just one final value as the prediction, right? We saw how we can design the type of optimizer that we want to use, right? And how we train the model and how we make evaluations in the model, right? So basically that's what we have done so far. Now what we can do is try to get like a better prediction, right, for this model, make the model more robust to also make more better estimates for the test data set, right? Any ideas how we could potentially do that based on the things that we have tried so far? Any ideas? Like we did a bunch of stuff like in the feed-forward neuronal network, right? And like all those things that we tried in the feed-forward neuronal network, all those tricks, like, oh, I'm gonna let it train for longer, more epochs. I'm gonna try to change the optimizer, you know, like, so all those things they apply here, right? So for example, the thing that I try, the approach that I try next is first to change from stochastic gradient, which like has all these problems that we discussed before, to something that's like it's more modern, right? Which is Adam, which is like my favorite type of optimizer. So now everything like above these points is exactly the same that we saw before. So the same type of look back, right? I'm gonna define the model just like as we did before. So it's a sequential with like 4 LSTM blocks. It's still outputting a single value, right? Now the optimizer is going to be the add-on. So like the add-on has all these momentums and so on. Okay. Let's see how this model performs with that. The loss,
changing the learning rate.
I also changed, yeah, I also changed the learning rate, I think. Yeah. I think before it was 10 to the -2. Yeah.
Yeah.
So I also changed the learning rates. So like, but yeah, absolutely. Changing the learning rates is also something that's usually that was one of the things that we'll do, right? Which like to try different learning rates. We'll do this type of like screening for like the appropriate learning rate. But yeah, that's also something that you can do. And there's several other things. I'm just using 4 LSTM blocks. By all that means you could be using like 100 if you want. It's just gonna take much longer to train, right? So, okay, here's the add-on, right? So you can see that the add-on is performing is slightly better. So like the R-square that you're getting for the test set is 0.6 now, right? And like for the stochastic gradient, it was 0.45. So like add-on once again beats the stochastic gradient, okay? So that was one of the things that we did now. So there are several other things that you can try next. So for example, so far in this example, we're using one time point to predict the next one. But as we said, you can use as many time points in the past as you want, right? Which now is basically the window method. So you use a whole window in your data to try to predict the next time point. So let's see how it performs now. So the look back now is going to be 3. So I'm going to be using 3 time points to predict the fourth, basically. Okay. We do the creation of the data set with this new look back. So now the data looks like that. Okay. So like now I have in train X, I have these 3 time points, right? To predict the next one, which was 0.04. Then for the next one, you see that I shift everything to the left, right? To predict the next one. So like, I hope this idea of like what you're trying to do in formatting this table is clear to everyone. Okay, so everything else is the same. So the optimizer here, here I'm just setting the optimizer to add-on, which is slightly different from the way how you're defining before. So that's just another way. Before I was directly specifying the optimizer and the learning rate. But if you don't want to do that, the TensorFlow, oh my God, it's such a hard word for me. TensorFlow also gives you an option to do that in a shortcut, just like as we did for the mean square error, right? So you can just call add-on, and this is going to use the default. This is going to use the default learning rate for you, which is 10 to the minus 3 as well. Okay. So by all that matters, by just calling optimizer equal to add-on, we're doing exactly the thing that you're doing before by calling the specific optimizer in TensorFlow, right, with a specific learning rate. So like this is exactly the same thing.
In this case, the learning rate is like this.
Is the default, which is 10 to the minus 3 already. Like there I was basically just saying like, I was using that huge syntax to just import the default configuration of add-on. Yeah, but that's a way how you can play with like the parameters. Okay, everything else is the same. So let's see how the model performs now. So actually, if you look at the absolute numbers here, you're gonna see that we start to present some hints of overfitting, right? Because like the performance for the training set actually got better, right? In the meantime, the performance for the test set got worse. So that's a very strong evidence for some degree of overfitting happening there. You guys remember what overfitting is, right? Just 1 second. You guys remember what overfitting stands for, right? What's overfitting? Yeah. Yeah. And usually the consequences that you generalize poorly for like unseen data, right? Which the test set in this case, and that's what we observe. So like, then something needs to be done. There are things that we could do here. For example, regularization. We saw like dropout, for example. You guys remember of dropout, where you like randomly remove some nodes of your network. Dropout is also implemented for TensorFlow. So you can add like dropout in a layer that you're defining. Although I don't use here, but it's also something that you can add there. Very well. So like, actually the window method for this configuration didn't work as good, right? So if we can try to, yeah, sorry, I forgot about you. Yeah.
So we have lots of one kind of ones they're waiting to say.
So it's not this, they're features, right? And like, since they are features, each feature is gonna have a weight that's gonna be trained to try to combine those features in order to approximate your target set, right? So like, we see that like the training process is gonna associate different values for the features in this case. Yeah, but initially, yeah, it's a random distribution. The weights are initialized as a random distribution. Yeah.
It would be that you start learning only a little bit which loss of station to express and things like that.
Yeah, yeah. No, so but that's just like using the default configuration, right? So like with 4 LSTM blocks, you can make the model more complex, right? Because the theory says that if you keep increasing the complexity of a neural network, right? Because the neural networks, they have this property of being universal computational engines, right? You should get closer and closer to a better prediction. but with the trade-off in mind, which that like when you make your model more complex, it also favors overfit. So like you have to keep balance of each of them. Roland?
That's one question to this window variable. So if I enlarge my window, wouldn't I also apply in this moment some kind of a low pass filter? Because, yeah, because if I look at a greater amount of data in the back, wouldn't I eliminate the influence of higher frequencies lower than the scale of the window?
Perhaps, yeah. But one of the things about the high frequency of your data, right? So what was the whole assumption of LSTMs, right? What we were discussing before, that we assume that the transitions, they are sort of smooth, right? So if I have data that's high frequency, that means that I'm oscillating a lot, which is something that LSTMs, they're not very good at, right?
Yeah, I have to replace this kind of window by some kind of turning rate or sometimes then.
Yeah. Because like LSTMs, they are a good fit for modeling like sort of continuous data, right? So like, although if you look at this data here, you say like, oh, but super high frequency, but like between neighboring time points, actually the change is pretty small, okay? So like the data is still pretty smooth, although in the big picture, it looks high frequency.
Yeah, because it seems that the STM couldn't raise that fast than the original data. So
Yeah.
it seems to be a frequency problem parallel to low pass.
Yeah, could be, yeah, because like we saw that when you're using just one time point to make the prediction was actually better, right? So, yeah.
We have to increase the data size. More stations, but that's this balance, I think, prediction.
Yeah, you could increase batch size. Yeah. Definitely could increase batch size. There's so many things that you can do different, and I hope you guys doing the exercise. Yeah, there are several things you can play with. Cool, great questions. Any other questions before we move on to the next case? All right, so now we have been dealing with this data as I described to you here, right? Which was that we had features that are now representing previous time points, right? So those, by all that means, they are features, right? So they are not actual timestamps. They are features that are being used to predict the next time point. Can everyone see how these like? This is just like the type of data that we used before for random forest, neural network, right? But they're not effectively being considered by the model as timestamps. Okay, so by all that means there's so for LSTM to consider them as timestamps. Okay, there is one more thing that you need to change. So the format of the input by default looks like this. Same time steps by features, right? Which like in this code, there was this one thing that apparently nobody asked about, which input shape. Okay, so the input shape tells me like it's organizing number of time steps, right? And number of features. So that's how I tell the LSTM what's the format of the data that this thing is about to see. Okay, so how was the input shape defined before? The input shape was, okay, I have one time step, right, with this number of features. So I have like 3 features, which is essentially what you have there, right? So now we're going to say like, now use this data effectively as those points that I'm giving to you as time steps and not as features of the data. Okay, so it's a slightly change of approach. And now let's see how that helps with the model or not. So the only thing that changed in comparison to the previous definitions, right, is that the input shape now is different. The look back is exactly the same. Okay, so you can see that the shape of the variables changed as well. And again, it didn't help that much. So like apparently using the data as like features versus time steps that didn't make much difference for the current configuration. Okay, so the idea here is just to tell you like that there is another way of framing the problem. Instead of like dealing with previous time points as features of the data, you can pass them specifically as time steps, which might be desirable for a specific application that you have, right? What is the difference between what we are doing like now of passing like time points as being features versus time steps? So for example, when you have a data that is temporal, okay, that has more features. So let's say we're talking about the rainfall before, right? In my very naive description of what are the features that usually matter for predicting rainfall, right? And we listed a few of them. So in that case, I already have features that are associated to each measurement, right? So my data, my observations that are temporal in this case, they are all time steps. So like, because in this example that I have, I only have one variable, which is just like in this case temperature. I'm allowed to go back and forth between like how I'm going to use the data as features versus time steps. But in this other case, the rainfall case, the features are already defined because I have those features that I'm going to use as predictors, right? So I don't have that flexibility, and that's why I wanted to use like a 1D data so we can go back and forth. Okay, but like in different case, for example, Jitska was mentioning like if I have satellite image from vegetation changing over time, my features there are the pixels, right? So like the features are already fixed, and then the only flexibility that I have is like in terms of time steps. So like the time steps I would be able to play with, but the features don't. Okay, is that clear? Like what's the difference between the two approaches, time steps versus like features? Good. Good. Memory between batches. Let me see if I have something more interesting. Yeah, let's go to this one. Let me just explain very quickly what means memory between batches. So another thing that PyTorch does by default to you, and in TensorFlow, you have the option to remove, is the assumption that the batches they are independent from each other. Okay, so what does it mean? If I give you like a stack of observations, right, a stack of rows, like in a table, I assume that this stack of rows to the next stack of rows that I'm going to feed in, they have absolutely no relationship between them. So like they're individual observations that I'm going to use to train the model. Okay. Now, if your data is temporal, is sequential, and is smooth, right? That's actually not the truth, because like the first stack of rows, the first observations that you have, they are to some extent dependent on what's gonna conditioning what's gonna happen next in your table, right? Because like it's temporal data in the end of the day, right? So you might benefit from actually keeping some memory about what happened with the previous batch. Okay, if you don't do that, by default you just train the model as you have been doing so far, which like you do a full pass, you update the weights, and then you move on to the next pass, and you don't pass any other information besides the update of the weights that you have. But you can keep track of previous gradients as well, which is like some degree of memory between batches that might benefit your application. Okay, but for other types of data where like you don't have any dependence between rows, that's not something that makes sense at all. So by default, this thing is always false, right? But like when you have temporal data, you have the option of setting that to true and keep track of what happened in the previous batch. And that's essentially what we're going to try here. So like this is the feature that you control via setting the state to true. So stateful true means that you're going to keep track of what happens to the previous batch. Let me see if which makes it perform even worse. So that's not good either. But the thing that like we have discussed before, right? Which the increasing the complexity of the problem. It's something that so far we have been using just like 4 blocks of LSTMs to model this time series, right? You can also, the same way how we used to add hidden layers you can also add more LSTM blocks, right? So here we are stacking more LSTM blocks. So you see that like in the first line, we had these 4 blocks of LSTMs, right? The second line, we had extra 4 blocks of LSTM, and finally we have this dense layer that's gonna give us the final output, okay? And everything else is the same, besides that I'm training the model for longer. I didn't plot the, yeah, I didn't plot the curves this time, but like by the numbers here, you can see that like that increase even further the effect of overfitting, right? So you see that the R square here is like got much higher for the training set and lower for the test set. So like that was also not something desirable. One thing that I don't remember if we did in the feed for network was to add early stopping. Did we do that? The early stopping, which means like train the model, right? So far, we have been setting the number of training iterations, which are epochs, to a fixed number, right? And then you say train this model for like 100 epochs, right? But what if by forcing the model to train for all these epochs, right? So like, again, what the curves they look like for overfitting in general, right? So if this is lost, this number of epochs, right? It has said that like one very classic example of overfitting is when your training loss looks like this, right? And your test loss looks like like this. This is the classic overfitting. And when you see that, there is a big variable, right? But what if you can cheat in the system, you know, like, and stop the training right here? So that's essentially what the stop does for. So like what you do is like, okay, I keep track of what's the validation loss in my test loss. In the moment that the loss is no longer going down, I say like, oh yeah, this is going to start overfitting, you know, like, so I can just stop right there. So like in this case, for example, if you use like these very big models, which at some point is like overfitting, right? You can try to cheat the system by saying like, I'm going to use this very big model, which gives more capacity to what I'm trying to model, right? Gives me more capacity, and I'm going to try to cheat the overfitting like behavior of this model by stopping when I see that the loss is no longer going down. And let's see how we do that. Yeah, so now we have to add like some extra functions, right? So for example, here I'm saying that the early stopping, I'm going to be keeping track of the validation loss, because that's what effectively matters for me, right? When the validation loss is not going down, I stop the mode. The mode is the minimum. So like that means that like whenever I reach the minimum and start going back up, I start counting how many epochs this thing is no longer getting good, and then I stop. And now finally it's like, what's the patience of my model? So like, let's say that my model, I'm gonna let it train for extra 3 or 5 epochs, and since I saw the last best loss, right? So like when it starts going up again, I count like, okay, 5 epochs. If it's not improving, I kill it, right? So that's the patience. Okay. And now you need to save this model, because like this model, in general, the way how it was training before, this neuronal network will train for all these epochs, right? And then after the training is over, you just run an inference, right? But now we need to save that state, right? So like now we need to also save a checkpoint, and that's what we do in the next line. So now I define this model checkpoint function, right? I mean, I'm not defining, I'm just importing that. That's also in TensorFlow already. And I'm gonna say that's the path to where I'm gonna be saving the model. So that's, I have a folder models, and that's the name of the model that I'm gonna save, right? I'm monitoring validation loss, like the minimum validation loss. That's where I'm gonna use as the criterion for my early stopping, right? And I say that I want to save the best model only. So like I could save in checkpoints. So like I would save the model every like 5 epochs, but like I don't care about all these intermediary like training steps. I just want the best model that they can get. So I just save the best model. Yeah, please.
What are the other options?
Yeah, the thing is that for the early stopping, you can use more metrics besides the mean square error, right? So let's say that like you don't care as much about like minimization of a loss, but you actually have like a specific target in mind. Let's say that I want to maximize the R square performance. So like I would give this metric. I didn't define that here, but like I could say that the metric is gonna be, yeah, the correlation coefficient, right?
So it depends on the measurement.
Yeah. Yeah. So the for early stopping, you can use absolutely anything. Like, and TensorFlow gives you a bunch of options. So
Yeah.
Yeah. Good question. Any other question?
Expectations, is that the number of extra efforts or just like 100?
Oh, 100 is a lot. Yeah. Yeah, it's supposed to be less. 100 is a lot. It's the number of epochs that you're going to keep training after you have observed the last best performance. 100 is a lot. Let's see. Yeah, so basically the early stopping is not doing anything in this example, because you see that I'm training for 100 epochs, right? And then I say that the patience is 100. So like, yeah, it's not really going to do anything. Okay. Cool. Any other question? Yeah, you can need more one. All right. Oh, yeah. Okay. Yeah.
Then already one foundation to see what the foundation was in the first training. And then people go and do the echoes.
Right.
The same thing is each time we're done with one echo or no?
Each time what?
Each time we're done with each iteration of the echo, we say what we have so far.
In each iteration of the epoch, you check if there was improvement to validation loss. And then if there is improvement to validation loss, you say the checkpoint of being the best mode so far.
And this is the iteration number, or what do you say? That's the check mark with the.
Yeah.
So because before the plot we show is going to be on the x-axis was the number of echoes. Right?
Yeah.
So we're going to say this check mark would be the echo path that we have this.
Yeah, I mean, you don't keep track of where in airport wise it happens. You just care for the best mode, right? But you can say also, like, for example, another thing that I put that there is that the last parameter that I gave you model checkpoints is set best only, right? Another option would be to save the model as just checkpoint. So let's say that you're going to train your model for like Google does, you know, which like 1 billion endpoints. You know, if something goes wrong in the middle, you want to make sure that you have some checkpoints, so you can resume from that checkpoint. So this function is more general. It's not just like to say the best model per se, but it's to say the checkpoints. So like you could do that like checkpoint twice. So like every 5 epochs to save any checkpoint. Is that what you're asking?
Yeah, no, so already, I don't know, we could say actually the whole model at this point, right?
All the ways of the model, yeah. Yeah. Because, yeah. All the things that you need in order to restart the model or.
But it goes to start in different prediction. I was wondering, right? If you do that, another sample prediction, what they say in model SM NCM, this is your out of sample prediction.
Same prediction.
Out of sample prediction.
Out of sample, yeah, this is based on validation, yes. But you can say the checkpoint is also based on the training logic. This makes less sense. Okay, we're very close to the end. I know you're tired. I'm tired. Okay, so that's how this training session was going. Here I'm using Adenine once again. Let's see if there was any improvement. The model performed worse again for this approach. Let me see if there was one combination. I tried a couple of things last night. Let me see if there was one that was performing better. Oh yeah, this one actually performed good. Let's see what I was using here. Okay, can someone describe to me what was this model? Let's go over this model that seems to be the most successful so far. So this one had R square for the training set, for the test set 0.73, which I think is the best so far. And you see, very interesting, right? You see that the training, the R square on the training set, it's a little lower, 0.86, right? So like, that's actually a good sign. That means that like, you're not modeling 100% the training set, but actually generalizing, like finding like some common rules for the data in general, right? I think I was talking about that with Chobin yesterday, right? So yeah. So that's usually like what you observe. That's like the performance on the training set is not as good as in the case when you're overfitting, but like you also have better performance for test set. Okay, yeah. So tell me what are the characteristics of this model here? Okay, so I'm using look back equal to 3. What does it mean? I'm using 3 time points, right? Okay. Now let's see next. Yeah, so the data is organized as the following, right? So it's samples, time steps, and features, right? So time steps here is equal to 1. So that means that I'm using my data as features, just like that. Because like from what we have seen so far, apparently using previous time points as features seems to be more beneficial for performance. Okay, what about the model? No, first the early stopping. So what am I using for early stopping here? What's the metric that I'm keeping track of to infer the best point? The validation loss, right? Since it's validation loss, we assume that the point of lowest loss is the best point. So we want to use as mode the minimum loss, right? Verbose equal to 0. So I don't want this thing to be plotting lots of stuff. The patience, once again, I messed up. I know I didn't mess up this time. Yeah, it's 100, but the number of epochs is 1000. So we are good. Okay, so good. Once we go to model checkpoint, right? I'm just saving the best model. I don't want to be saving like several models like throughout training. Very good. Cool. So what am I doing here now? I'm creating a model, right? That's how I initialize the template using sequential. Then I start stacking LSTM blocks. I'm using 8 blocks for the first cell. Then I'm using another 8 blocks for the second cell. And then I give one final value as the prediction, which is basically what we have there. All right. Then what are the definitions? Like what am I going to use for optimizing this model? So I'm going to keep track of mean square error, right? And the optimizer, once again, is Adam, because Adam rocks. Then we're going to do the fitting of the data. First part's training data, the labels associated, which labels here like are these T, given the information from T minus 3 all the way to T minus 1, right? The total number of epochs this time is 1000. I was using just 100 before. And validation, that's my validation set, text X and text Y. Oh, I didn't tell you guys how you will give the callbacks as input, right? So we defined up here these early stopping the model checkpoint, but I didn't tell you where you give this information to the model during training. So you pass as callbacks, which are like functions that you feed into the model as well. And then you just list them, very simple like this. So ES is early stopping and this is model checkpoint. Okay. And then you train this model just like as we did before. So this is like doing the inverse of after you do the prediction, you inverse it back to the original domain and so on. And yeah, that's basically was the best configuration that I got. But with a big group like this, if you guys keep playing with the parameters, I'm pretty sure we can find something even better. All right. Yeah. So you see that like my patience is set to 100, right? I think I put it here somewhere. So this model was supposed to go all the way to 1000, right? But it stopped here at something like close to 200, right? That might be 190 or so. But since the best model is the patience was 100, in reality, the best time point is this minus 100, right? So might be around here. So I think this was the point that we got the lowest loss. Does it make sense for everyone? Yeah. Good.
So the only two differences are this, the number of epochs, that is 1000 right now,
Yeah.
and the number of blocks.
The number of blocks.
That's what you change.
Yeah. Correct. Yeah. So I increased the complex of the model and I added early stopping because I'm cheating, right? Like I'm doing the thing like, oh, I see that it's going to start overfitting. So I stop it before it's actually overfits. So that's it. That's the closest that you get to a free lunch in machine learning is to use early stopping. Like that's the closest you get. And okay, yeah. So now I have this other data set that I also got from Kaggle, which is like a pollution data set. So it has like more features to it. So like before we didn't have features. We just had like one variable that we're keeping track, right? Now we have features. So like we have other stuff there. Let me see if I can visualize it. Yeah. So for example, we have the date from that measurement, the amount of pollution, which I think is here is measured as ppm. Then you have temperature, pressure, wind speed, if it was snowing or raining, wind direction. The wind direction initially is like formatted as being like actual direction, like in cardinal directions, but and then here I transform that to like numbers because neuronal networks, we need numbers. We cannot work with like categorical variables, right? So what I propose to you guys is that you now play with this data set and try to use the same techniques that we covered in the tutorial, you know, make the model complex, epochs, like play with the different type of optimizers, and be happy, I guess. Yeah. So
Is that available?
yeah, I'm gonna send it to Pepe and Pepe puts it there, right? Yeah. Yeah, we're gonna put.
It's not yet.
No, I didn't pass it. Yeah, it's not there. Sorry.
We can do now.
Yeah, we'll do now. Yeah. Let me see if there are questions first. Yeah. Any questions? But good questions. Yeah. Thanks for talking to me.